And along with the summary, I want to start building a diagram over here of all the spherical Coxeter groups. And I'm going to add to the diagram very slowly, so you can leave some space, and eventually it will be this big. Okay, but now I'm going to start over here. So here's a summary from last time. So from last time, we had a classification of the regular polytopes. And I want to write them in a slightly different way. What I want to do is I want to write 6 lines. And on each line, I want to put a particular type of regular polytope. And so the first line, I just want to put the n-gons. On the second line, I want to put the n-simplices. The n-simplex. The third line, these are the 3 infinite families. The third line, I want to put both the n-cube and the n-orthoplex. These are duals of each other, and I want to put them on the same line. N-gons are self-dual, simplices are self-dual. And then we had 3 types, or I should say, the reason why I want to put the ones that are dual to each other on the same line is that if you think about the symmetry group of the cube and the symmetry group of the octahedron, they're the same, right? Because any symmetry of this is going to send the centers to the centers and is therefore going to be a symmetry of this, right? And vice versa. So the group of symmetries and the group of symmetries are identical, right? That's why I'm putting them on the same line. To continue, then we had, so these are the infinite families. And then we have exceptional cases. And there were 3 exceptional cases. There were these 2, the 12 cell and the 20 cell, Dodecahedron, Icosahedron. Let me just say 12 cell and 20 cell. Then when we went up a dimension, we had the 120 cell and the 600 cell. And then we had the 24 cell. Okay, and if you look back at the classification, these were the only ones. And so in terms of the groups, in terms of the isometry groups, we have 3 infinite families and 3 additional groups, right? Okay, and the first thing I want to do is I want to actually give you names for the groups. And let me first write down the diagrams, since that's the way we've been describing them. The diagram in the first case is very straightforward, just looks like it, oops, let's try that again. I reordered my list. The diagram in the first case looks like this. The diagram in the second case looks like this. And you remember that missing numbers mean 3, right? So this is 3 through 3 through 3. And in the third case, it either means this or written in the other order, right? I won't write both, I'll just write the one. For the exceptional ones, they were very specific. They were this or in the other order. This or in the other order. And that one. What I want to do now is I want to give you the names for these, and the names are going to be, are going to not make sense. The names will not make sense yet. In fact, they will look very random. Those are the names of the 3 infinite families. Okay. And for these last 3, okay. And in fact, what you should really be thinking of is that this is not so much a name for the group, this is a name for the diagram. Okay? This is because what's going to happen is that either late today or first thing tomorrow, we're going to start talking about Lie groups and Lie algebras and other objects, and they will also have names like this, and they will also be classified by diagrams like this. And so the diagram will on the one hand refer to the Coxeter group, to the Lie group, to the Lie algebra, but the diagrams are what they have in common. Okay? And so the strange names refer to the diagrams, and so if you really wanted to talk about the groups, you could do something like this. You could say, I'm looking at the Coxeter group of type I2M, the Coxeter group of type AN, the Coxeter group of type BN, the Coxeter group of type HN, the Coxeter group of type H4, or the Coxeter group of type F4. And the general name, so the general name, what some people sometimes do is they just say Xn, where X stands for some letter and N is some number. Okay? And then over here, the polytope is P. And the name for the diagram is often gamma. Okay. All right, so those are the names. And now I'm going to write those names over here. And I'm going to label one of my circles. So at the end of the first part of the talk, what we'll have is we'll have a complete picture of all spherical Coxeter groups, and the ones that are in this circle are going to be the ones that are from regular polytopes. Okay, the left-hand circle are the spherical Coxeter groups that come from regular polytopes. Those are the only ones you've seen so far. And partly what I'm hinting at is that there are others. And once you see the others, then actually the names will start to make more sense. Because the ones that are missing are called things like DN, E6, E7, E8. There's a G2 that's missing. And in fact, let me go ahead and mention some special cases, because these categories are not completely independent. There are overlaps. Right? There's some overlaps. This is the symmetries of the regular n-gons. These are symmetries of cubes, but you can look at a two-dimensional cube, and that's a square. Right? And so one thing to note is that I24 is the same as B2. Right? I24 is the same as B2. These are symmetries of the square. And in fact, maybe rather than writing down the diagrams, let me do it with the groups. So the Coxeter group of type I2B4 is the same as the Coxeter group, or I24 is the same as the Coxeter group of type B2 is the same as the isometries of the square. Okay? The Coxeter group I23 is the same as the Coxeter group of type A2 is the same as the isometry group of the equilateral triangle. Right? And the last thing that I want to put up here is that, well, you actually know what these groups are, right? Symmetries of polygons. What groups are those? Dihedral, right? These are the dihedral groups, right? Those are the dihedral groups, and then, so this is the dihedral group of, so this one's actually a symmetric group, right? This one's the symmetric group on three things with 6 elements. And in fact, if you think about it for a second, this, in general, the symmetries of an n-simplex, of a nice regular n-simplex, what symmetries can you have of this? You can permute the 4 vertices however you want, and you get a nice metric preserving transformation, right? And so the symmetry group is actually the full symmetric group. The symmetry group is the full symmetric group. But one thing you need to be slightly careful about is that when I write down A2, so this is A2, right? Because it's a two-dimensional object. How many vertices? 3. When I write down this one, A3, three-dimensional object, number of vertices? 4. And so when I write down that this is the symmetric group, yeah, it's the symmetric group on n plus 1 things, right? There's an extra, yeah, n plus 1 things. Okay. Yeah, maybe rather than messing up our chart, maybe I'll put that down here. So, notes. But I forgot to do my third. Okay, so symmetric group on n plus 1 things. The other thing that I wanted to introduce is that there's one more of these that has a special name. And the reason for this is that if you think about, this is looking ahead to what we're going to be doing next. I told you we were going to do 2 days on the spherical Coxeter groups. And so today and tomorrow we're supposed to be talking about Euclidean Coxeter groups. Right? So we're switching from regular polytopes, and we're going to start talking about Euclidean tilings. We're going to talk about ways of tiling the plane with the same size shape. Okay? So if you think about the regular polygons, if you take a triangle and you start reflecting in its sides, an equilateral triangle, and you reflect in its sides, you get a nice tiling of the plane. Right? You can get a nice tiling of the plane with copies of a triangle. You can also get a nice tiling of the plane with copies of a square. Right? There's one more shape that has that property, one more regular polygon. That's the hexagon. Right? And so the hexagon gets a special name. So I26 is one that's special, and this one gets called G2. It's the Coxeter group of type G2, and I want to go ahead and add it to my picture. I left a space for it. And up here, so A2 is the same as one of the i's, B2 is the same as one of the i's, G2 is the same as one of these. And so let me go ahead and put a little star here, where the star means m is not equal to 3, 4, or 6. Okay? Because when m is 3, 4, or 6, it's equal to this one, or this one. Okay? And the reason why 3, 4, and 6 are separated out is that 3, 4, and 6, this other circle is going to be ones that extend to tilings of Euclidean space. Okay? And if you think about polygons that are not triangles, squares, or hexagons, you can't use a pentagon to tile the plane. You can't use a heptagon to tile the plane. You can't use any other regular polygon to tile the plane, and so all the other polygons go over here, but triangles, squares, and hexagons go over here. Okay? All right. Similarly, if you look at these groups, the symmetries of the Dodecahedron and the Icosahedron, these groups also do not extend to tilings of 3 space. Okay? And that's why the H3 group is over here. Okay? All right. Next. Okay. Yeah, that's everything from the first page. All right. So, the next thing that I want to bring up is that I want you to think for a second about the proof from Friday. Well, how did the proof go on Friday? We said we started with a regular polytope. We subdivided it so that it was broken up into chambers. The chamber, we took all the hyperplanes and we came up with the root system. And then from the root system, we wrote down a matrix, and then from the matrix, we wrote down a diagram, and then we started classifying. We had bad diagrams, and then we just said certain diagrams are good, certain diagrams are bad, and we had a little flow chart that said we found them all. We found all the good diagrams. Right? Suppose I had a collection, suppose I had a diagram, and there was only one place in that process where we used the fact that we started with a polytope. And that was that at one point in the proof, we said because it's a polytope, most of the angles are pi over 2. Right? We said that if we have VI and VJ and there's a VK in between, then there was going to be an orthogonality relation. And that used the structure of the polytope. And so then we knew that we only had, most of the angles were non-trivial, and so all of our diagrams looked like straight lines. Right? But what if I could give you a diagram, and actually this is such a diagram. This is a diagram that's not a straight line like this, but this does encode some 4x4 matrix. Right? You can use the exact same procedure and go from this picture to a 4x4 matrix. Right? You just number the vertices and you just go ahead and fill in all the things. Where in each entry you either put a 1 on the diagonal or you put cosine pi minus pi over m, where m is whatever the label is. In this case, all 2's and 3's. And what I want to claim is that the 4x4 matrix that you get that's encoded in this picture is a positive definite matrix. Okay? The 4x4 matrix encoded in this diagram is a positive definite matrix. So what does that mean? That means that because this corresponds to a matrix which is positive definite, that says I can find, because the matrix is positive definite, I can find 4 vectors in R4 with the appropriate angles. They actually exist. Those 4 vectors determine 4 hyperplanes that give me a little simplicial cone. It really exists. With all the dihedral angles, pi over m's. And so I can start reflecting in the sides, and I can sweep out a nice structure. Okay? And so from this picture, I can work my way back, and I can get a finite group generated by reflections of spherical isometries. It's just that it's not coming from the symmetries of a regular polytope. And you can tell that it's not coming from a polytope because it has a branch in it. Right? If it came from a polytope, it would look like this, just a string of numbers. So this is not from a regular polytope, but it is a perfectly good finite group generated by reflections. And because it's positive definite, it really does correspond to a similar kind of group. Okay? You can go from the matrix to the vector arrangement to the hyperplanes and then get the group. Yeah? It's just that it's not from a polytope. And so what I want to do next is I want to extend the proof that we talked about last time to a few more cases. And so now we're no longer going to talk about polytopes. We're just going to say, let's just say, let me put up some additional good diagrams. And what do I mean by good? By good, I mean what I meant over here. That if you take the diagram and you build the matrix and you calculate the determinants of the principal minors, they're all positive. So it really is a positive definite matrix. It really does correspond to an arrangement of vectors in space. Okay? So here are some additional good diagrams. There's one called DN. And you make it as long as you want. Okay? So it's almost like AN. It's almost like AN, just has sort of an extra edge coming out. Okay, that's called DN. There's going to be one called E6, which, you've probably noticed somewhere along the line, the subscript indicates the dimension of the polytope. It also indicates the number of reflections. Right? I mean, there's lots of things that are subscript. And so when I write DN, this is supposed to be 1, 2, 3, 4, 5, 6, 7, N. Right? Okay. E6. So this is something with 6 dots. And again, this is something where you can actually just check. You write down the matrix, check whether it's positive definite. It is positive definite, but because of this branching, it's not coming from a regular polytope. Okay? E7 is sort of similar, and E8 is similar. Okay. All right. So those are additional diagrams, and corresponding to these, there's additional groups. Right? One thing that I should actually say is that, well, I'll come back and talk about the groups, but each of these diagrams corresponds to an arrangement of vectors, corresponds to a fundamental chamber, and when you reflect in the sides, corresponds to a finite group generated by those reflections. Okay? And they go on our picture. There. Okay. And so they're outside this circle because they're not coming from regular polytopes, but they're inside this one, and I haven't really told you what that is, but I'll tell you what this circle represents in just a second. At this point, the name should be closer to making sense, because if you stare at the ones in this circle, that almost makes sense. Right? Because what do we have? We've got some A's and some B's and some D's, all infinite families. And then we've got a special one, E8, E7, E6, F4, G2. Right? A, B, D, E, F, G. Right? Why does it almost make sense? We're missing C, right? Okay. We'll come back. There is no C. Or another way to say it is that Cn and Bn end up being the same. But I told you that the things in this circle are going to be related to Euclidean tilings. The things that I've got written down are representing finite Coxeter groups. They're representing things that are fixing a point. And what happens is that the type B, the symmetries of the cube, has two ways that it can extend out to being a tiling of space. And so when you take the symmetry of a cube and you try to extend it out to a tiling of space, there ends up being a B type and a C type. And when we extend it to all of space, what we're going to do is we're going to take these old names and we're going to add little tildes on top. We're going to add a little, we're going to have things like, so instead of AN, we're going to write AN tilde. Instead of BN, we're going to write BN tilde. Except there's also going to be CN tilde. Okay? And then from DN, we'll end up going to DN tilde, etc. Okay? And so these are going to be the Euclidean Coxeter groups. Okay. All right. So let me just say it that way. These are the ones that are coming from Euclidean tilings. These are the ones coming from Euclidean tilings. And so every spherical Coxeter group, every tiling of a sphere by simplices with nice angles, either comes from subdividing a regular polytope, or it comes from some nice spherical tiling, or Euclidean tiling. Okay. All right. And what happened in terms of the history was that the first things that were named were the Euclidean tilings. AN tilde, BN tilde, CN tilde, DN tilde, E8 tilde, E7 tilde, E6 tilde, F4 tilde, and G2 tilde. Those are the only Euclidean tilings by simplices. We'll talk about these a little bit later. These are the only Euclidean tilings by simplices. And then for each one, there's a corresponding finite Coxeter group. We'll talk about that. And when you go from this list, so this list goes A, B, C, D, E, 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 F, G. Right? That list makes more sense. When you go from here down to the finite ones, B and C collapse. And so we only have B, we don't have C. But then when you're looking at the finite ones and you're not worrying about tiling Euclidean space, then there's others that show up. And at that point, it makes sense to add the next letters. H, I. Right? And so then the names make sense. But when you only look at this list for the regular polytopes, you've sort of lost the history. This was the first thing, this was the second thing, this was the final thing.
When it was spherical Coxeter groups,
yes.
they are the complete list.
The complete list.
Definition of spherical.
Yeah, okay. So the definition of a spherical Coxeter group. Actually, let me hold off on that for just a second. Let me hold off. Because one thing that I want to do first is, like we did with the polytopes, with the regular polytopes, what I want to do is I actually want to at least quickly sketch the proof that this is a complete list. Okay? Because the proof scheme is the exact same thing. What was the proof scheme for the regular polytopes? We had good diagrams and we had bad diagrams. And then we just run through the possibilities and make sure your list is complete. And so what I want to do is I want to give you additional bad diagrams. Something like this, something that's in a cycle. This is a bad diagram. Okay? This is something that you haven't seen. Everything you've seen so far is either in a straight line or it has a little bit of branching. And part of the reason why those are the only ones that show up is that this is bad. Cycles are bad, and so what does that mean? First off, what does it mean to be bad? It means that this diagram encodes a matrix that is not positive definite. Right? But if you look at sub-matrices, if you remove some of the vertices, that looks like a something. Right? And so all of its sub-matrices are positive definite, and so all of the principal minors will have positive determinant. The only thing that fails is when you take the determinant of the whole thing. And what happens is that this turns out to have determinant 0. Okay? If you put 3's all the way around. You can also put bigger numbers. And if you put bigger numbers, then you get negative determinant. Okay? But 3's or bigger, these are always bad. Okay? All right. Well, once you know that that's bad, what's the only possibility for the diagram? If there are no cycles, it's a tree. All right? So this implies gamma's a tree. Right? Okay, let me give you some other bad diagrams. Other bad diagrams. Well, we already know from last time. I should give this one a name. This one is called A n tilde. And because A n tilde showed up, you should be thinking that this is going to come back. Right? This actually is, with 3's all the way around, this is the A n tilde that corresponds to a Euclidean tiling. And if you look back at the bad tilings from last time, there were some bad tilings from last time called C n tilde, where you had a number bigger than 4 followed by a bunch of 3's, followed by a number bigger than or equal to 4. That was one of our bad diagrams from last time. If you actually let it equal 4, this turns out to have determinant 0. And this turns out to be the diagram for the C n tilde Euclidean tiling. Okay, we'll come back and talk about that in a second. Another thing that was from the list before, so this is from last time, there was also an F4 tilde and a G2 tilde from last time. And the F4 tilde looked like this. The G2 tilde looked like this. This was from last time. And now that I've introduced G2, We never actually drew the diagram for G2. What is the diagram for G2? G2, this one, it's just a single edge with a 6 on it, right? 6 representing hexagon. Yeah, okay. So when you look at this, this looks like AN with an extra vertex. That makes it into a cycle. This looks like G2 with an extra vertex. This looks like F4 with an extra vertex. This looks like Bn equals Cn with an extra vertex. Okay? All right. Well, so once you have this, you know that it's a tree. Once you have this being bad, that says that you can't have more than one edge with a high label. Right? Let's say the label is high if it's bigger than 3. This says you can't have 2 high labels. Right? That's how we used it before, but we can also use that in a tree. Because given any 2 high labels, you just connect them up with the shortest path, and you have a copy of this inside your tree. Yeah? Okay. So there's at most one high label. Here's another one that's bad, and it's called Bn tilde. So this is a branch point, and then somewhere else a high label. This also is bad, and it's bad even if it's a number bigger than 4, and when you make it exactly 4, then that's going to be the label, the diagram called Bn tilde. Okay? So this says no cycles. This says you have at most one high label. This says that you can't have a high label and a branch point. So now you have to choose. Either you have a high label or you have a branch point. If you have a high label, you have no branch points, it's going to look like a straight line, and it's going to be the old case. Right? And so what we're reduced to is that now, having already dealt with the no branch point case, this says that we have no high labels. And it's really just a graph with 3's everywhere. Okay? All right, then we have something called Dn tilde. Actually, let me start out with D4 tilde. D4 tilde is a very nice little picture that looks like this. So let's see, Cn implies at most one high label. Bn implies high label or branching, but not both. D4 says branch points have degree 3. They can't have degree 4, or you could select out a diagram that looks like this. They can't have degree 2 because then it's not a branch point. Right? Okay. I'm running out of room, but let me just go all the way to the corner. Dn tilde is sort of this picture, but where there's more in between. And so what does this say? You can't have 2 branch points. And so now we're getting down to being quite restrictive. Right? So, by going through these different bad diagrams, there's no cycle, so it has to be a tree. There's no 2 high labels. There's no high label if you have a branch point. We already did the no branch point, so we're down to just no high labels. You can't have high degree branching, and you can't have more than one branch point. And so the only pictures we have left kind of look like this. One branch point going off in 3 directions. And then there are 3 more bad diagrams. Let me go ahead and I can get rid of this. Okay. And they're called E6 tilde E7 tilde, and E8 tilde. And again, one thing that I pointed out before, I said that the F4, that when you don't have the tilde on top, F4 has 4 vertices. The tilde has 1 extra vertex, right? And so F4 tilde has 5 vertices, right? And so this one called E6 tilde should have 7 vertices, and it does, right? Okay. There's E7 tilde. And then, oops, yeah, that's correct. One, two, three, four, five, six, 7, 8, 9. And the final step is just to say, if you've got 3 branches, if you only have 1 branch point, all the labels are 3s, how long can these things be? Well, if they're both very short, then you're going to be good. Then you're going to be a D, right? But if they're all at least 2 steps, then you're going to have this in there. And so at least one of them has to be short. Okay, but 2 of them can't be short because you'd be in this case. And so what about can the other 2 both be long? No, they can't have 3 vertices on each side because you'd have this. And so one of them can only have 2 vertices. And so you've got 1 vertex on one of the branches, 2 vertices on the next branch. And then how long can that last one be? Well, it can be up to there. And when you go through the possibilities, what's left is E6, E7, and E8. All right? So similar kind of thing, similar kind of argument. You have things that are good, things that are bad. But along the way, notice that we actually ended up looking at number of diagrams. I didn't say this, but when you look at if you calculate the determinant of this diagram, all of the subdiagrams are good. Right? If I remove a vertex, that's E6. That was one of our good ones. Right? If I remove the middle, well, then I get an A2, an A2, and an A2, and they're all perpendicular to each other. Good, good, good. In a two-dimensional thing, it's going to be good. Right? Every subdiagram is good. And so all of the principal minors will have positive determinant. Why is this bad? The determinant of the whole thing is bad. And what I haven't told you is that this determinant is determinant 0. This determinant is similarly, all the subdiagrams are good, the whole thing is bad, and its determinant of the entire matrix is 0. This is determinant 0. That's determinant 0, that's determinant 0, that's determinant 0 with a 6, that's determinant 0, this is determinant 0 with 4s, this is determinant 0 with 3s, and that's going to be relevant, and those are the diagrams that correspond to Euclidean space. Okay? Because, now let's go ahead and start talking about that. All right, but hopefully with this very similar argument from Friday, you can at least believe that this is a complete list of diagrams that correspond to positive definite matrices. Right? This is a complete list of diagrams that correspond to positive definite matrices with our particular rules of turning diagrams into matrices, where we put 1s on the diagonal, we put cosine pi minus pi over m off the diagonal. Yeah, where m is an appropriate integer coming from the diagram. Okay, so the next thing that I want to do, and you asked me for a definition of spherical Coxeter group. Okay, I need to not forget that. I don't want to tell you yet, but I want to not forget it. Okay, so all right, so the next thing I want to do is I want to look at a particular triangle. I want to look at a 30, 60, 90 triangle. So pi over 2, pi over 3, pi over 6 for the angles. Okay? So this is a nice Euclidean triangle, And all of the dihedral angles are of the form pi over m. Right? All of the dihedral angles are of the form pi over m. And if this was on a sphere, what would we do? If this was on a sphere, we would say, write down the hyperplanes and take the normal vectors pointing inside, and we'll get an arrangement of vectors. Well, just to make it easier to see, rather than taking the vectors pointing inside, I want to take the vectors pointing outside. And if I take all the vectors pointing inside and I reverse all the directions, the angle didn't change. Right? Because as long as I change both, it's the same angle. It's just easier to visualize that than having them all cross through the triangle. Yeah? Okay. That's an arrangement of vectors in space. Right? That vector, and that vector. That's an arrangement of vectors in space. What's the angle between these two vectors? Pi over 2. Right? How about here? Pi minus pi over 6. Right? How about here? Pi minus pi over 3. Right? This is an arrangement of three vectors where the angles are all correct. If we were going to draw a diagram for this, what diagram would we have? Let's go ahead and give these names. Let's call this I don't know, how about U, V, and W? I don't want to use subscripts, so I just want to, because it's not coming from something. Let's just call it U, V, and W. And so I've got three dots, U, V, and W. The angle between U and V is going to be an edge labeled 6. The angle between U and W is pi over 2, and so I'm just not going to put anything. The angle between V and W is going to be a 3, which we don't label, and so I actually could just have drawn this like this, right? U, V, W. And so what diagram is this? This is G2 tilde. Right? This is G2 tilde. And so now you have to think back to the linear algebra statements that I gave you on Friday. I said that if you have a positive definite matrix, real symmetric matrix with these special, if you have a positive definite real symmetric matrix, then that corresponds to a linearly independent arrangement of vectors. Well, what's happening here? It's positive semi-definite. Every pair of vectors forms a basis. Every pair of vectors is linearly independent, but all three, they're linearly dependent, and because they're linearly dependent, when I write down the matrix, I'm going to get a 0. Okay? And so the 0 from the determinant corresponds to the linear dependency of the three vectors. And so there's a slightly more complicated statement that one can make that if you have a matrix, a real symmetric positive semi-definite matrix, if you have a real symmetric positive semi-definite matrix, then you can construct an arrangement of vectors, but now it's going to be linearly dependent. Okay? And with positive semi-definite, the ones we're going to look at are actually positive semi-definite, but every submatrix is positive definite, which means we're going to get an arrangement of vectors so that they're linearly dependent, but anytime you remove one, they're linearly independent. Okay? And now we want to start talking about things that are tilings of Euclidean space that look similar to the tilings of spheres. And so we want to start with a Euclidean simplex. Let me say it this way. If we have a Euclidean simplex so that all of the dihedral angles are pi over m, then we can reflect in the sides and it will tile space. If we start with a Euclidean simplex where all dihedral angles are pi over m, then we just reflect in the sides and it tiles space. Okay? And in fact, those are going to be the only Euclidean tilings that have simplexes as a simplex as its fundamental domain. And so then we want to start classifying Euclidean simplices with pi over m dihedral angles. And so when you start looking for diagrams that have these diagrams as subdiagrams but have determinant 0 on the top level. And when you try and classify those by a similar kind of argument, which this time I'm going to skip, but by a similar kind of argument, you end up finding that these are the only diagrams of that type. Okay? So let me actually just write this down because it's a helpful and useful fact. Okay. That these four infinite families and these 4 infinite families and these 5 unusual ones, special groups, are, sorry, I need to add one more that you haven't seen. And this is going to look a little bit strange, but there's a diagram called A1 tilde. And this is one that you haven't seen. But this is one that we can actually visualize, because A1, what was A1? The subscript represents the dimension, right? So what was A1? A1 was the interval, right? A1's the interval. And so what are the outward pointing vectors? The outward pointing vectors are this one and that one, right? And so we've got the blue vector and the red vector. What's the angle between them? Pi. Right? And if you want to think of pi as pi minus pi over something, pi minus pi over infinity. Okay? So they really do have angle pi, and so we're going to put an infinity there. Okay, so the diagrams A1 tilde, AN tilde, BN tilde, CN tilde, DN tilde. Here's AN, here's BN, CN, DN. And I erased D6 tilde, 7 tilde, 8 tilde, but and there's F4 and G2 are well, let's say 2 things. They are 1. Descriptions of the angles between the outward pointing normal vectors or outward pointing vectors normal to the facets of a Euclidean simplex in which all dihedral angles are of the form pi over m for some m in the set 2, 3, ... union infinity in that one special case. Okay. And the fact that this description applies to all these really just means that when you write down those diagrams, subdiagrams are positive definite, the whole matrix corresponding to the diagram has determinant 0. From that fact, that implies that you can actually go and build something like this. The second claim is that this is a complete list. Of simplices with these properties. Okay. All right. So A1 tilde, AN tilde, BN tilde, CN tilde, DN tilde, G2 tilde, GF4 tilde, E6 tilde, E7 tilde, E8 tilde. So these are the spherical Coxeter groups, and these are the Euclidean ones. Okay. So, is the statement clear? That the example you should be thinking of is think of like a 30, 60, 90 triangle. This is a triangle, it's a Euclidean triangle, and all of the angles are of the form pi over m. And because of that, when you reflect in the sides, you're going to tile space. And if you look at the normal vectors will be linearly dependent because there's going to be one more vector than you have dimensions. And if you look at all but one of the normal vectors, then what are you doing? If you only look, let's do this for a three-dimensional thing. If you have a tetrahedron and you look at the four normal vectors, you know that because you have four vectors in R3, it's linearly dependent. If you only look at three, let's say you only look at these three, how do you know that they're linearly dependent? Well, they're the hyperplanes that intersect at this point. They bound a nice little triangular cone. That tells you they're linearly independent. Right? Similarly, if you take these three, they correspond to this vertex. Those are linearly independent. These are linearly independent. These are linearly independent. And so the fact that you have a simplex actually in front of you in space tells you that subsets are linearly independent. Okay? All right. And that the whole thing is linearly dependent. And the proof that this is a complete list is just very similar to the ones that we've done. Okay. There are three Euclidean triangles that are very nice that you've been studying since high school or earlier, right? What are the three Euclidean triangles that are really, really nice that have angles that are nice? Well, there's the 30, 60, 90. I don't know if that's the name you call the triangle, but pi over 2, pi over 3, pi over 6. What are some other ones that are nice that you study all the time? Yeah, 45, 45, 90. Or pi over 4, pi over 4, pi over 2. Right? And the equilateral one. Right? Pi over 3, pi over 3, pi over 3. All three of these will give you nice tilings of space. And each one, now that you're getting used to this, you should be able to draw diagrams for. And so this one we said was G2 tilde. What's this one going to be? There's a 90-degree angle, so it's going to end up being a straight line, right? Because there's going to be a 90. And then the labels, 4, 4. And so which pattern does this look like? Yeah, so this is C2 tilde. Okay? Because this is so 45, 45, 90 is this diagram, which is this pattern. Okay? And then this one, with pi over 3, pi over 3, pi over 3. It looks like this. Actually, let me draw it like this, just because there's a temptation to think that the vertices correspond to the vertices, but that's not what's going on, right? The vertices correspond to the sides, right? Because the vertices correspond to the vector, which is a normal vector for one of the hyperplanes. Okay, so this would correspond to that side, this would correspond to this side, this would correspond, it would correspond to this vector, and that vector, which would correspond to the three sides, and so on. And what is this? A2 tilde. Okay. Yeah. So the three two-dimensional Euclidean Coxeter groups are A2 tilde, C2 tilde, and G2 tilde are the names. Okay. All right. So what I've done is I've postponed, I want to call you Sam, Professor Kim's question for a while. We haven't yet defined a spherical Coxeter group, and now we have also not defined Euclidean Coxeter groups. Right? Okay. So now let's define both. Okay. All right. And let me start with a few observations. All of the isometries of a sphere form a group, right? If you think about the isometries of a circle, they form a group. You can compose. You think of them as functions. But what are the rigid motions of a circle? There's lots, right? You can flip it around in any direction. You can also rotate various amounts. But with any rotation and any flip, you can compose them and you get a nice group, right? It's a slightly complicated group because how many elements are in there? Infinite, right? This is an infinite group. In fact, if you think about cardinalities, is this a countable group? Is this the size of the natural numbers? No, because you can rotate for any real value. So this is the same size as the reals, right? And in fact, this one in particular you can actually think of as a picture. You can sort of say, it ends up looking like this, where these end up being the reflections. And this is the identity. So you start here, and if you rotate, you move somewhere on this circle. And if you reflect, then you end up somewhere over here. Okay? That one dot for every reflection, one dot for every rotation, and then you can start moving around. This is sort of a picture of the group. Okay? That as and so this is sort of a very special object in that even when you talk about high-dimensional spheres, like S2, where you talk about where you can rotate like this, you can rotate like this, you can flip across equators, isometries of spheres are two things simultaneously. On the one hand, they're a group with a continuum of elements, right? Same size as the reals. It's a group that's a continuum of elements, but if you look at the group, it's also, if you start at the identity and you look close to the identity, that looks like the real line. Topologically, it looks like the real line. In terms of the analysis, it looks like the real line. In higher dimensions, the isometry group of S2 will end up looking locally like R3. Okay, the isometry group of S3 will locally end up looking like R6. That every point will have a small neighborhood that looks like Euclidean space. And the word for that is that this is a manifold. Every point has a neighborhood that is homeomorphic, is the same topology as Euclidean space. Okay? And so this is a group that is also a manifold. It has a topology. There's a notion, it has a metric. There's a notion of closeness that you could put on this. We haven't talked about the metric, but you can put a metric on this as well as there's a, yeah. So this is a group. It's also a manifold. And let me just give you a quick definition of a Lie group. A Lie group is a group which is a manifold and the two structures are, I'll just say, compatible. And what I mean by compatible, is that when you multiply by a group element, it should take points that are close to points that are close. It should preserve the notion of limits, that if you have a sequence of points limiting to a point, their image under the group action should limit to a point, right? That group multiplication should be a continuous function from the thing to itself. All right? Okay, so a Lie group is a group that is simultaneously a manifold. Another example, and a slightly easier one than I've written over there, is the... All right, so when we talk about spheres and isometries of spheres, metric preserving maps of spheres, that big group actually is a Lie group. Okay? It's a group that also has a manifold structure. And because the set of isometries is a Lie group and it has this manifold structure, it has a natural topology. And let's see, I'm assuming that you guys have seen a little bit of topology. A set, so if you have a subset of Euclidean space, it's called discrete if there are no limit points, right? Or said differently, that you can find neighborhoods around every point no limit points. Yeah? So a subset of Euclidean space is discrete if the induced topology is the discrete topology. Okay. Slightly fewer nods, but it's still okay. So what is a spherical Coxeter group? A spherical Coxeter group is a group inside here, generated by reflections, and it's a discrete subgroup. Okay? There's a notion of closeness here, and you want it to be a discrete subgroup. What that ends up meaning in practice is that you don't want to have a hyperplane and a hyperplane and a hyperplane where they start limiting to one another. You don't want to have a sequence of hyperplanes that are getting closer and closer. Right? You want your hyperplanes to be nice and separate. Okay? And so it just happens to turn out that if you want to look at a discrete, so maybe I should write this down. So a spherical Coxeter group is a discrete subgroup of the isometries of an n-sphere generated by reflections. Okay? And it turns out that requiring the subgroup to be discrete, in this case, this turns out to be a compact manifold, and so discreteness ends up forcing it to be finite. And so all of the groups that we have listed here turn out to be finite groups. All right, and hopefully you can now guess the definition of a Euclidean Coxeter group. What would be the definition of a Euclidean Coxeter group? It's a discrete subgroup of isometries of Rn generated by reflections. Right? We just replaced the sphere with Euclidean space. Yeah. So let me just do this in a different color. So Okay? But otherwise, it's the same definition. A Euclidean Coxeter group is a discrete subgroup of the isometries of Rn generated by reflections. I might actually need to be slightly more careful than that, but that's a good first approximation. There's something that I'm thinking about in the back of my head, but let me go ahead and stop at that. How are we doing on time? 5 after. Okay. Did that. We did this. Okay. Great. Yeah, given that we have 8 minutes, I'm going to do one small thing, and we'll come back to it next time. Okay. So I guess I should mention, when I say that I want your short paper to have something about each of the different, this is the list, right? The dihedral groups A and B, and these are the groups that I want you to talk about. Okay. All right. Oh, and if you want to try and, one way to try and find these names that I've been using, the A, B, C, D, the names, this is called, the names are called Cartan, Killing type. Cartan and Killing are two mathematicians. Cartan, there's actually two Cartans, L.A. Cartan. There's a father and a son. They were both mathematicians studying Lie groups. Killing was a German mathematician slightly earlier, 1880s. And so the two of them are the ones that are responsible for these names. All right. So the small thing that I wanted to do was that, just to make a quick remark, it turns out to be true that a spherical Coxeter group extends to a Euclidean Coxeter group if and only if every label M is in the set 2, 3, 4, 6, infinity. Okay. So this is not something that I'm going to prove as a deep fact. This is something that we're just going to observe from the list. We have a complete list. We can look, and what you'll see is that the label here, M, if it's 2, 4, or 6, then it extends. It's one of the others. Why are these excluded? Well, this one has a 5. This one has a 5. That's why they're excluded. And there is a slight reason why those matter, and this might look like a strange set. It probably does look like a strange set of numbers, 2, 3, 4, 6, infinity. Right? But it's not that strange if you observe the following. Let me go ahead and write down the numbers 2, 3, 4, 6, infinity. And then what I want to put in the next column is I want to put a value that comes up. So I'm going to let me just write theta where theta is pi minus pi over n, just to make this a little bit easier. And what I want to write down is 4 cosine squared theta. Okay? And if you think back to your trig identities, like the double angle formula for trig identities, sometimes 2 cosine is easier to write than cosine. When you look at the double angle formulas, there's often a 2 in the denominator. And if you write it for twice cosine, it's sometimes much better. And in fact, if you think about the circle, what is cosine? Cosine is this distance. What is 2 cosine? 2 cosine is that distance. Right? That actually makes a lot more sense geometrically to focus on. So sometimes it makes more sense to focus on 2 cosine than on cosine. Right? All right, so let's go ahead and try this list. So it is 4 cosine squared theta, where theta is pi minus pi over m. So in this case, it's 0. Okay, that one was easy. Right? What happens here? When m is 3, then we're going to get 2 pi over 3. Actually, what's going to happen? The pi minus, cosine of pi minus is the same as negative cosine. But I'm squaring, so the negative goes away. So I might as well just forget the pi. Right? So 4 cosine squared pi over 3. 4 cosine squared pi over 4. 4 cosine squared pi over 3. Or 6. 3. That these are the only m's such that 4 cosine squared pi minus pi over m is an integer. And that's what makes these m's special. Okay? It can't be bigger than 4. It can't be smaller than 0. And so there's these 5 possibilities, and these are the m's that produce these 5 possibilities. And that's what makes them special, and you need this sort of integrality. You need these sort of integers to show up in order. Deep in the theory of Euclidean Coxeter groups, you need lots of integers to show up. And so you need this condition, and so that's why this turns out to be true. All right, I'm out of time. I'll start here tomorrow.